Hello, chemistry class. Happy Tuesday. I hope your day's going well. Today is going to be a little bit about nuclear technologies, and then later you'll get to watch some of a movie about radioactivity. Okay. So we've been talking about these different kinds of radioactive decay. And right now we're just going to focus on the third one we've learned about called gamma emission, right? Where gamma rays come out of an atom's nucleus when it breaks apart. So remember, right, you have this part of the nucleus that's coming out, but then you also have really high energy that's coming out when an atom is radioactive and unstable. Okay, so you've seen this before. This is just showing the different kinds of energy we find in our universe, and that these rays that are coming out of the atom are called gamma rays, and they're super high energy. So one of the highest forms of energy we know of. And that property is part of why we use radioactive elements for things like nuclear power plants, because a lot of energy is coming out of those atoms. So if we can harness that energy, right, we can use it to power things like homes and factories. Okay. Another reason that we use radioactive elements for things like power plants, we've talked about before actually, and it has to do with Einstein's equation, E equals mc squared. Okay. So remember we talked about before that sometimes mass can actually turn into energy. So this is a weird idea that something that exists, like part of an atom, can instead turn into energy instead of being that thing anymore. So that's basically what happens when radioactive atoms break apart, right? Some part actually comes out, but a little bit of that nucleus, which I didn't tell you about before, a little bit of the nucleus actually turns into pure energy. So it's no longer existing as matter. Now it's just energy. Okay. And this is where that equation E equals mc squared comes in. So that little bit of the atom that turned into energy, right? Originally it was mass. And what Einstein figured out is that anything that has mass, we can calculate how much energy it's going to produce by multiplying its mass by the speed of light squared. So that's what that C is. C just stands for the speed of light. They just chose that letter to represent it. So you can see it's a pretty big number. It's 299 million meters per second, approximately, with a little extra, right? And so remember, squared means this number multiplied by itself. So we're multiplying 299 million times 299 million. That's going to make an even bigger number. Okay, sorry, I'm recording this from home and my cat is playing with a cat toy. So we have this huge number, and now we're going to multiply it by the mass that came out of this atom back here, right? The mass that came out of here. And even though that mass is very small, we're multiplying it by a huge number. And so we're still going to get a pretty good amount of energy just from that one piece of the atom. Okay, so that's what I just explained, right? Because this is a big number, you multiply that by a small amount of mass, you're still going to get lots of energy just from that one atom. And so that's what happens when we have radioactive elements. We have, right, a bunch of radioactive atoms they're breaking apart, there's stuff coming out and turning into energy, and so they actually produce quite a bit of energy. And so nuclear power plants use both of these kinds of energy, both the gamma rays that are coming out and the energy that comes from part of that nucleus. And what we do with that energy is basically we use it to heat up water. Okay, so in this picture, this is a very simplified version of what a nuclear power plant does. So basically on the left side here, you have these little rods, and that's where the radioactive elements are, okay? And they're surrounded by a bunch of water. And so they're breaking apart, they're making lots of energy and heating up that water. And then the heated water goes over here to another container. And what happens when water heats up, right? It makes steam. So there's steam coming out of this superheated water. And we use that steam to turn some kind of device like a turbine. Okay, except in a real power plant, the turbines are larger. Okay, they're not this like tiny looking fan here. They're really big. So we use steam to turn these giant turbines, turn these like gears and wheels and stuff. And eventually we can turn that into electricity. Using something called a generator. So we turn the turbine, that thing turns a generator, which if you were in physics last year, you learned a little bit about, and it has to do with magnets. When we turn magnets, they make electricity. So we've got all these things going on to create the product we want, which is electricity for our homes and cities and towns. Okay, so the radioactive elements that get used most often are uranium, sometimes plutonium. You can see these are very large atoms. The nucleus is not even shown, but imagine, right, for uranium, there would be 92 protons and somewhere around 140 neutrons, I believe, instead of this one pink circle. And then these are all the electrons on the outside. Okay, so pretty big. The thing is that these types of elements, they do break down naturally, but they don't do it quickly enough where we could actually use that to generate electricity or power. So we need a way to make them break apart faster than they would naturally. Okay. And so this is what we do in nuclear power plants. Basically, we take a neutron and we shoot it at a uranium atom. And every time that happens, the uranium atom releases more neutrons, and those go on to hit other uranium atoms. And so we call that a type of chain reaction, right? Where you get one going, and then that one sets off another reaction, and those set off other reactions. So that's what's happening in a nuclear power plant. We're making a bunch of uranium atoms or plutonium atoms break down really, really quickly to make lots of heat. So this idea of making atoms split apart is called fission. And you can see this is going to go on to create that chain reaction. So fission is different from another idea we've already learned about called fusion. This confuses people a lot because those words sound really similar. So I'm going to try to teach you a trick so you can remember the difference. Okay, so fission, that's what we just learned about, right? An atom breaking apart. Fusion is the opposite of that, where you have protons and neutrons coming together, sticking together to make a bigger atom. Okay, so this one is an atom breaking apart into smaller pieces. Fusion is smaller pieces coming together to make a bigger atom. And you could maybe remember that by remembering part of the word fusion. fusing together, right? Fusing is another word for like joining together, gluing together, right? So we're fusing atoms together to make new ones. Okay, so fusion, fusing. If you can remember that, then you'll always remember, oh, fission's the opposite of that. That's the one where it breaks apart. Okay, so we use this process to make electricity in our power plants. We've also used this in the past to make atomic bombs work, which is what the movie you'll watch today is about a little bit. Okay, so imagine, right, we have radioactive atoms inside of a bomb. So this is one of the real bombs that was used in World War II, unfortunately, in Japan. But inside they put radioactive elements. And basically they knew, right, that if they could set off this chain reaction inside the bomb, lots and lots of energy would get produced all at once. And that's what you're seeing here in this giant explosion. Okay, so what happens when you create lots of energy at the same time and just let it out into the world without controlling it? You're going to get a ton of heat and a ton of radioactive atoms going into the air. So not the best idea for more than one reason. Some of the potential dangers of nuclear power, which you're probably familiar with, there's kind of two main things that we need to keep in mind with nuclear power. One is the possibility of a nuclear meltdown happening. So basically, this is where you have a nuclear power plant, right? And because we're making those atoms get so hot to produce energy, we have to make sure that the things they're in don't get too hot, because if they get too hot, they can actually melt the structures around them. And then all of a sudden we have a bunch of radioactive elements that are breaking down and we can't control them anymore. So once they get out of here, out of this like containment structure, that's not good, because we can't cool them down anymore or get them to slow down. They're just going to keep going. Okay, so sometimes that can happen. Luckily, it's only happened a few times in human history so far. So there was the 3 Mile Island incident. That was the first time something like this happened. And that happened in our country in 1979. It also happened in the Ukraine in 1986, and that's what we call the Chernobyl nuclear accident, which you'll hear about in the movie. And then the most recent one happened in Japan, which you might remember even though you were quite young. In 2011, the Fukushima nuclear power plant had a meltdown. Okay, so these things happen if we don't manage the power plants properly. If we're not keeping these things cool, sometimes they can run out of the stuff that's used to cool them, right? And if we don't notice that, then something goes wrong. The other main thing about nuclear power that could be negative is, right, after we use those nuclear or those radioactive elements, even the stuff that's left over is radioactive as well. And so we can't just, right, leave those things wherever. We have to make sure that they're stored safely where they can't accidentally get out into the environment, where they're not around where people are to affect them. And so there's very few places that we can store these things. A lot of the nuclear power plants around the world have only temporary storage facilities right now. So they'll put these used nuclear rods that have the radioactive elements in them, and they'll put them in giant pools of water because that keeps them cool and kind of keeps those radioactive atoms inside the water instead of getting out into the air and stuff. But we can't keep them in these forever. Eventually, they have to go into a more long-term place And so we need to bury them deep underground. But there are only a few of these facilities in the world. We don't have enough to store all of the spent nuclear fuel that we currently have. So that's a problem. We need to find more places where we can bury these things very deep underground. Okay, things that are radioactive, they're not always bad. I don't want you to grow up thinking, oh, everything radioactive, that's bad. Because we can use these things with no harmful effects to humans. Okay, it just depends on how much we use, which kinds we use, how we use them. And so one example is in the medical field, we can actually use radioactive elements to see inside of people's bodies so we can figure out what is wrong. Maybe there's something wrong with their body. We don't quite know what it is. We can use radioactive elements to see what's going on inside there. And we can use them to treat diseases sometimes. So the amount that we use for things like that is so little that it doesn't harm that person's body. So next, I'm going to have you watch a couple videos just on nuclear medicine because it's cool. So go ahead and watch those. And then when you're done, you can put your Chromebook away.